Hi everybody, so for this lesson what we're going to do is work through the assigned problems and just kind of go over all the solutions for them. So in the assignment that I posted on the Google Classroom, it tells you to do problems 53 through 55 and then numbers 71 through 84 I think, and we're just going to do the solutions to all of them. It's going to end up being a really long video. So you can just try the problems beforehand and just kind of skip around to the parts that you didn't get or that you need help with. The grade for this lesson, or the only thing that I'm actually going to look at, is the quest assignment. So kind of just do this until you feel good with some of the circuits work, particularly the parallel circuit problems. And once you feel comfortable and you feel ready, go for try the quest assignment. And as long as you get an 80 on that, I'll give you credit for the unit. So let's go. 53. A 6 ohm and a 4 ohm resistor are connected in series to a 5 volt power source. Okay, we have a series circuit with multiple devices, and as always, that's going to be a verb chart for us. We've got the first resistor, the second resistor, and that's it, and then our total column. Alright, so let's fill in whatever we can here. We have a 6 ohm resistor. We've got a 4 ohm resistor, and then we've got a 5 volt power source. And we're going to find the total resistance of the circuit. So this is a series circuit, and we'll always double check our rules for series and parallel circuits. Your reference table says that for a series circuit, that's this one right here, to find the equivalent resistance, we just add the first one, plus the second one, plus the third one, and so on. So that's all I'm going to do here. I'm just going to say that the total resistance is equal to the first one plus the second one, or 6 ohms plus 4 ohms. So when we do that, you get 10 ohms. Great, that's our total resistance for this series circuit. The total current of the circuit. Alright, total means this row down here, and I want the current, which is this box. It looks like I know V and R. So I can use that to find the current. R equals V over I. R is 10 ohms. Again, stay in that row. Equals V, which is 5 volts over I. And when you do that, you get I equals, cross multiply carefully, I got 0.5 amps, or half an amp. Just going to fill that in down here. 0.5 amps. Alright, last up, the voltage drop across the 6 ohm resistor. So we want the voltage across the 6 ohm resistor. I think that's this box in our verb chart right there. Okay, looking at this row, I don't think we know a whole lot about that row, but what we do know is that in a series circuit, the current is the same through every device. I'm looking at this line right here. So what that means is I can put in 0.5 amps here and 0.5 amps here. And alright, now I think we're all set, because in this row right here, we know the current, we know the resistance. We can just do Ohm's law, R equals V over I. 6 ohms is equal to, we're solving for V, whoops, we know the current is 0.5 amps. Alright, cross multiply, and I got a voltage of 3 volts. And there we go. Nice quick verb chart for series circuits. Alright, 54. 2 resistors, each with a resistance of 6 ohms, so it looks like each of the 2 resistors has the same value, are connected in parallel to a voltage source. So this one's going to look a little different from the previous one. Again, we're still going to do a verb chart, so I'm not even going to read the question yet. I'm just going to make a verb chart. With 2 resistors, and then the total. I'm going to fill in what I know, and then I'm going to take a look at what we got. Because again, this is kind of just how we do these problems. Alright, oops. I know that we have 2 resistors, each of them are 6 ohms. I think that's it. Alright, a little weird, but we'll see how this goes. We're going to draw a circuit diagram. Okay, so we should have a voltage source, which is just a battery. And we've got a 1 resistor, and then a second resistor. There we go, that's our parallel circuit. Again, if you traced along from the battery, you follow the wire, and right here you've got an option which way you want to go. You can go this way, or you can go this way. That's what makes it a parallel circuit. The fact that there's more than one branches, more than one paths to go through. Calculate the equivalent resistance of the circuit. Alright. This is probably the easiest one to get wrong, because sort of the knee-jerk reaction would be like 6 plus 6, well that makes 12. And then we're good here, but that is wrong. It's not correct. This is not a series circuit. This is a parallel circuit. And in a parallel circuit, remember this rule that we went over in the last lesson? We have to do this whole thing. There's no real way around it. So that's what I'm going to do. I'm going to do 1 over Req is equal to 1 over R1 plus 1 over R2. Alright, plugging in 1 over 6 plus 1 over 6 ohms the unit. 1/6 plus 1/6 is 2/6. Simplifying gives you 1/3. Now remember, that's not Req, that's 1 over Req. So 1 over Req is equal to 1 over 3. The last step to solve for Req is to flip both sides. Req over 1, which remember, anything over 1 is just itself, so I'm not going to write out that whole thing, equals, okay, 3 over 1 is 3. And that's my answer, measured in ohms. You should think about this for a second, because it should seem weird that having 6 ohms and then another 6 ohms gives you a total of 3 ohms, which is smaller. But remember, adding resistors in parallel makes the equivalent resistance smaller. This actually does make sense for a parallel circuit. And let's see what would happen if we kept going with that trend. So now what we'll do is I am going to add, let's change color, yeah, whatever. A third 6 ohm resistor is connected in parallel. So we're adding a resistor like here. And I want the new equivalent resistance. Alright, well, it's still a parallel circuit. We still have to follow that same rule. 1 over R1 plus 1 over R2. But the difference is now we have an R3 attached to it. Alright, we got to plug all of these in here. 1 over 6 plus 1 over 6 plus 1 over 6. Alright, 1/6 plus 1/6 plus 1/6 is a total of 3/6, which simplifies to 1/2. And again, just like before, that's not our answer. That's 1 over our answer. 1 over the equivalent resistance is equal to 1 over 2. So we got to flip both sides again. The equivalent resistance over 1 is equal to 2 over 1. Well, Req divided by 1 is Req, and 2 divided by 1 is 2, so the equivalent resistance is just 2 ohms. And again, I want to point out here, we added a resistor, but to answer part D, how does the total resistance of a circuit change when a resistor is added in parallel? So we added a resistor up here. We added another branch to the circuit. And I think that total resistance, if you look over here, it used to be 3, now it's 2. I think that total resistance decreased. Sort of a unique thing that parallel circuits do. If you add more paths, there's less resistance, because it's easier for the current to go through now. 55. 3 resistors, R1, R2, and R3 are connected to a voltage source as shown. On the diagram, draw an ammeter that would measure the current through R3. Okay, so we've got our voltage source here. Notice I gave you the values in the diagram instead of the problem this time. And we've got R1, R2, R3. We're going to draw an ammeter that would measure the current through R3. So this is R3 right here. And ammeters, remember, they're the ones that go in series. So I would like you to draw it either immediately before or immediately after. One or the other. You don't need both, so I'm going to erase one of them. But either one of them would have been fine. On the circuit diagram, draw a voltmeter that would measure the voltage drop across R2. So if it helps, I think I brought this up in one of the other videos, or in class the other day, voltmeters go in parallel. Voltmeters go in parallel with whatever they're measuring. So if we want to measure the voltage drop across R2, I'm going to add a voltmeter right here. There we go. Calculate the reading on the voltmeter from part B. Okay, again, it's a circuits problem. We're going to do a verb chart. VIRP. We've got 1 resistor, 2 resistors, 3 resistors, and then that total row, just like we've been doing every time. Oh man, I made this too small. There we go, now it's big. So let's fill in all of the things that we know. So I gave you all the resistance values in the problem. I gave you, one of them was 10 ohms. I gave you one of them was 15 ohms. I gave you one was 30 ohms. And then I said that this total voltage is 110. Alright, I want the reading on the voltmeter from part B. Now the voltmeter from part B is on R2. So it's going to measure the voltage through R2. That's this box right here. This one right here. And notice that we've got sort of a lot of blanks in the area around it, meaning we don't have a lot of information about that device. So we're going to have to really work our way around here. Let's just find anything that we can solve for, like just something that you can find. And for me, I'm looking at, well, if we know the first resistor and the second resistor and the third resistor, I think we can find this total resistance down here. It is a series circuit. Notice there's only a single loop. So I'm going to go to my reference tables, and it looks like to find that total resistance, you just do one plus the other plus the other. So that's what I'm going to do. I'm going to do 10 plus 15 plus 30, and when you do that, I got 55 ohms. Okay, cool. Again, doesn't quite get us where we need to be, which is all the way up here. But, I don't know, what's something else we can find? I'm looking at this bottom row. We know R, we know V. We can solve for I. We can always do that if we know R and V. We can always solve for I. R is equal to V over I. 55 ohms is equal to 110 volts over I. And when you do that, I got 2 amps here. Cool. Again, just one more thing that we know. It's always good to know more things. And I'm just going to fill that in kind of wherever I can. This is an example of a series circuit. For a series circuit, you get kind of more used to this as you do more problems. For a series circuit, that current is the same for every one of these devices. So I'm just going to fill in 2 amps, 2 amps, 2 amps. Alright, I think I'm finally ready to answer my question, because now we know R for R2, we know I for R2, and we're solving for V. So I'm going to do R equals V over I. 15 ohms is equal to, we're solving for V, but we do know the current through that device is 2 amps. Multiply across, and I got a voltage of 30 volts. Cool. Now, calculate the power dissipated by R2. So this is 30 volts. Okay, R2 is again this device right here. So for the power, I don't ask for that very often, but it's going to be the same idea. We are just going to stay in that row, meaning we're using this R2 row right here. Look at your power equations and find one that'll work. And really, since we know everything about R2, all of them should work. So I'm going to do, I'm just going to do the first one that's there, that P equals VI, because I think we know V and we know I. V is 30 volts, I is 2 amps, and you get, I got 60, and remember the unit for power is watts. 60, there we go, 60 watts. My final answer. Alright, according to the assignment I wrote out, the next question we're going to do is 74. Use the circuit diagram to the right to answer parts A, B, and C. So here's a diagram. And we're going to start with this. The most important thing you can kind of ask yourself when you get any of these circuit problems is which type of circuit is this, because that'll affect the rules that you do. Like, you might get it right or wrong if you sort of read it the wrong way. So for this one, I'm going to say it's a parallel circuit. And the reason I'm saying that is, if you come out of the battery, you're an electron, you travel along the battery, and see this spot right here? You can go through the 20 ohm resistor, or you can go through the 30 ohm resistor, which means this is an example of a parallel circuit. And we are going to keep that in mind when we do all of our rules. And since it's a circuit, we're just going to do a VERP chart. And then we have our total. Filling in whatever I can. It looks like I've got sort of like a weirder data set here, I think. We've got the two resistances, we've got the voltage. Actually, it's not that weird. Okay, so we know that the total voltage is 12 volts. We know that the first resistor has a value of 20 ohms. The second one has a value of 30 ohms. And I think that's it. I think that's all we know. Alright, first up, what is the equivalent resistance of the circuit? So remember, that's just the total resistance. That's that box down here. And I think I say this every time we've done a parallel circuit, but do not add the 20 and the 30. Because going back to our rules for a parallel circuit, you can't do that. You have to do this thing right here. 1 over R cubed equals 1 over R1 plus 1 over R2. So that is what we're going to do. 1 over RA cubed equals 1 over R1 plus 1 over R2. That's 1 over 20. I'm not showing my units because I'm going to run out of room. Alright, 1 over 20 plus 1 over 30. If you don't like your, fractions and common denominators, when you throw it in the calculator, I got 0.083 repeating, so let's put a couple threes there. And, again, that is not the equivalent resistance, that's 1 over the equivalent resistance. So, our last step will be to flip the two signs. I'm going to put the REQ on top, and then the 0.0833 on top. REQ over 1, which remember is just REQ, it's just the equivalent resistance, is equal to about 12 ohms. Again, thinking about your answer here, that equivalent resistance should be smaller than either of these two, because it's a parallel circuit. Adding those resistors in parallel makes the total smaller. So 12 is actually a pretty good answer for us. I think it makes sense. Okay, what is the current reading on the ammeter? This is the ammeter right here, and the first thing you need to do is think about which current does that read? Because it could measure the current through R1, or the current through R2, or the current through the total of the circuit. I'm going to say that it's measuring the current through this one right here, through the 20 ohm resistor. Because, you see how the battery gets the total current, right? So this would be like the branch of the battery. So on the battery we have all of the current, and then when we hit here they split up. We go through the ammeter and through the 20 ohm resistor. So you see how that's like on the same branch of the circuit? They have to have the same amount of current. And then some will go this way through the 30 ohm, but that would be different as well because it like split off. It's on a different road or on a different line of the circuit. So we're going to find the current through the 20 ohm resistor here. And again, we're missing a bunch of stuff that we're going to need, but in a parallel circuit, the voltage is the same through every device. So I'm going to fill that in for all of my devices. 12 volts, 12 volts, and now I think we're actually all set, because if I look at that top row, we know everything we need. R equals V over I. R is equal to 20 ohms. V is 12 volts over I, and when you do that, I got a value of I got 0.6 amps, 0.6 amps. Great. Total power dissipated by the circuit. I want the total power, so now I'm going to this box right here. We know V, we know R, we're solving for P. So let's go to our reference tables here. These are our power equations. We know V, we know R. So let's look here. VI, I don't think we know both of those two things. Right, we know V, we don't know R, so let's not use that one. I squared R, I don't think we know I, so we won't use that one. But I think we know V and R, so I think this is an equation that would work. P equals V squared divided by R. Great. We've got 12 volts, the voltage, squared. Again, I didn't show my units here. It was bad. But over 12 ohms. I'm going to show units. Volts. Ohms. Great. 12 squared over 12 is 12 watts. There we go. 75. A set of resistors is connected in parallel. Adding resistors to the circuit in parallel with the others will have what effect on the... So I've been trying to sort of bring up this idea a few times here. What I'm saying is we've got a battery, we've got a resistor, I don't know, and another one. And now what I'm going to do is I'm going to add an extra resistor in parallel. So I'm just going to add this branch right here. What does that do to the total resistance? The total resistance will decrease. And the reason it would decrease is this. You can imagine we're trying to fit a bunch of electrons through a loop. They're all trying to go from the start, and then loop around, and then finish. And then start, loop around, finish. And resistance is the ability to resist that. It's like how hard it is to do that. So, if you have one road for all these electrons, it's hard. And then if you had another road for all these electrons, it's... Well, wouldn't that be like a little easier? Because, again, you've got all these electrons. And if you just give them more options, we can fit more people through. In one of the previous lessons, we used the analogy of traffic. If you have more roads for people to take on their way home, everyone will get home faster. There's more places to put them all. So that's why the total resistance would decrease. The total current would increase. Two ways to think about that. One is you are resisting less, right? If the total resistance decreased, then the current should increase. Another way is if you kind of want to get there more directly, we've got some current through the first branch, some current through the second branch, and when you add another branch of current, there's more room for electrical current. So there should be more of that current since there's more room to put it. Total power. So the least obvious one here. A couple ways you can think about this. The first is total power is most closely related to current. Basically, whatever the current does, the power will do. And the current increase, which means the power will increase. If you don't like that, let's try something a little bit different then. Let's do P equals VI, right? Let's just pick the simplest power equation I can find. And we'll think about what's happening to all of these things. So for the voltage, but what's happening to the voltage? Meaning, what's happening to our battery source? Well, I didn't tell you it's changing, right? So let's assume that stays the same. If we have the same battery, it's the same amount of voltage. Alright, now the current, we just agreed in part B, should increase. So if you multiply the same number by a bigger number, you'll get a bigger number, or a value that has increased. Alright, for 77, the diagram below shows two resistors connected in a circuit. What is the voltage reading in the voltmeter? Alright, circuit analysis, right? We've done a lot of these in these videos. Verb chart. R1, R2, total. Now, I really like this question because it's kind of exactly the type of question that I would expect students to get wrong, like as you're learning this topic. But as long as you do the verb chart, you'll get it right. So let's make sure that we do that. Again, we just have to be really careful with this one, with like all the values that we use, and that they all match each other. And the easy mistake to make here is to use the 60 volt source with the 20 ohm resistor, but that is wrong. They do not match up with one another, so do not do that. So if you tried this question on your own and you got an answer of 60, then you did it wrong. So let's go through our whole verb chart and we'll see what we can do here. So for the total, alright, again, that's the battery, so let's go 60 volts. We've got a 20 ohm resistor, a 30 ohm resistor, And I want the reading in the voltmeter. So that voltmeter, it measures the voltage through this device right here. And, okay, and again, I think that's the 20 ohm resistor, so we're going to solve for this one right here. Alright, we got a lot of blank space to get to before we answer that, so we gotta find something, find anything. So let's do this. We know the 20 and the 30, let's find the total. But if we find the total, we gotta be careful what type of circuit this is. This is an example of a series circuit. Because if you come out of the battery, you go, now I want to point out that this does not make it a parallel circuit, this voltmeter. Meters do not affect the behavior of the circuit. So I know that voltmeter is there, but we can kind of like ignore it. It's like holding up a ruler next to something. That ruler doesn't affect the behavior of like whatever you're measuring, because I don't know, it's just a ruler. It's just kind of like next to it. And that's kind of the way that meters work for these circuits, without getting like too far into this. And then from there, you've only got one path, right? You have to go through this resistor, and then you have to go through that resistor, and then you have to go back to the battery. It's a series circuit. And I think you guys like those more because for series circuits, for that total resistance, we just add them all up. So that's what I'm going to do. 20 plus 30 is 50. Not going to show my work there because it's easy enough. Okay, now from there, what did I do wrong? Oh man, I'm sorry everyone. It was a 20 ohm and a 10 ohm. And then the total is 30. I apologize for that. Okay, so from there, okay, well, again, we still got a long way to go before we get where we need to be, so, I don't know, what's something we can find? Hopefully you're drawn to this row right here. We know the resistance is 30, the voltage is 60, so R equals V over I again. Resistance is 30, the voltage is 60. Solving for I, when you do that, I got I is equal to 2 amps. And the reason that's super helpful in this series circuit is that in a series circuit, the current is the same everywhere. So we can just kind of fill that in up through this whole row. Which means that finally we're ready to answer the question using that top row, R equals V over I. R is 20. V is what we're solving for. We know the current is 2. Multiply across and you get 40 volts for this device. And that is our answer. Alright, next up, another good one that I would kind of expect you to get, you know, it would be easy to make a mistake on, particularly if you don't use the verb chart. And again, the mistake, just reading quickly. The diagram below shows two resistors connected in a circuit. I want the current through the 5 ohm resistor. And again, the easy mistake to make here, if you were answering this very quickly, is to take this 9 volts and use it for this resistor. Can't do that, you'll get the wrong answer. But you'll get the right answer if you do a verb chart. So that's what we're going to do. V-I-R-P. Alright, filling in what we know. We know we've got a 4 ohm resistor, a 5 ohm resistor. We've got a 9 volt battery. It says 9 volts, I'm just really zoomed in so it's blurry. Okay, again, we want the current through the 5 ohm. That is this right here, right? The current through the 5 ohm. So just like before, you know, what's something that we can find? Well, I think we can find that 4 and 5 is 9 ohms. You'll notice that I just added those two together, and that's because this is a series circuit. It's a single loop for electrical current to flow through. And in series circuits, you are allowed to just add them. Again, think of what we can find. I'm looking down here, right? We know a voltage, we know a resistance. I think R equals V over I will get us there. 9 ohms equals 9 volts over I, and I think you get I is equal to, I got 1 amp. And so the question is, how does that help us? Well, it's a series circuit, right? And in a series circuit, wow, looks like those currents are the same everywhere. It's the same through every device. So this is 1 amps and this is 1 amps, and we answered our question there, didn't we? It was this 1 amp. I'm going to circle it. Cool. 79. A set of resistors is connected in series. Adding additional resistors to the circuit in series important, will have what effect on the total resistance of the circuit? Well, let's check our circuit rules. This is our circuit resistance rule for a series circuit. The equivalent resistance is equal to the first one, plus the second one, plus the third one. And let's kind of like not overthink this one here. If you've got a number, and then you add another number, and then I'm going to tell you to add another number to that number, wouldn't the value be bigger now? So the answer is increase. Series circuits are a little more intuitive than parallel circuits. It's this idea that if you force current to go through one resistor and then another resistor, and then you force it to go through a third resistor, that would be harder, right? Because you encountered more resistance along the way. That's series circuits. Remember, parallel circuits were sort of the weird ones where you added the resistors, but the total resistance went down. Alright, last problem for this video. It's one that I like because it's got a lot of devices. It's kind of a weird setup here. But if we do a verb chart, we can do anything. So that's what I'm going to do. But this verb chart is going to be sort of large. Because we've got not 1, not 2, not 3, but 4 different resistors. Oh no. But I do want to prove the point that these aren't any harder if there's more resistors. It's like a little more work because, I don't know, there's extra rows to fill in. But as long as you keep your same strategy, you could do this for like 100 resistors. I wouldn't do that to you, but you could. So, here we go. I'm going to fill in everything that we can. Again, kind of the same process every time. We've got 1, 2, 3, 4 resistors. I'm going to fill that in for all of these. And then this battery has 12 volts, so I'll fill that in as well. 12 volt battery. And then we've got 6 ohms, 12 ohms, 36 ohms, and then 18 ohms. Alright, I'm going to go ahead and actually fill in a couple more things, and what I'm going to do is take a look at the type of circuit we've got here. Come out of the battery, and oh man, see how we have a choice which way we want to go? That means that this is a parallel circuit. And in a parallel circuit, something's always the same, but it's not current, it's that voltage or potential difference. So what I'm going to do, just because it's so easy to fill in, is fill in all these 12 voltses. Okay, let's go. What's the current measured by ammeter A? So we're looking for a current, and I didn't tell you which resistor. I just told you it's going to be this device right here. So we have to think about that a little bit. Which device do you think that measures? I'm hoping that just kind of looking at it, see how it's directly next to the 6 ohm resistor, you know, there's no other like branches or anything near it. I'm hoping that you'll sort of get this idea that it's the current through that resistor, because that's the device that it's next to. From there, alright, we want the current, and it looks like I know V and I know R, so we'll keep this as simple as we can here. R equals V over I. 12 volts is equal to, whoops, no, 6 ohms is equal to 12 volts over I. I is equal to 2 amps. Awesome, cool, good work. We did it. Circle it. Great. So again, it looks like there's just so much more going on here because there's more numbers. Right, but that wasn't any more complicated than what we've been doing. What is the equivalent resistance of the circuit? Alright, well this one actually might be a little more annoying. Equivalent resistance, and again, do not add 6 plus 12 plus 36 plus 18. That is wrong. That's not how parallel circuits work. I'm going to go to the rules here. Always check the rules. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. Alright, so this one's going to be kind of a pain. But 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. plus 1 over R4. Oh man. Okay, I'm going to plug in my values. I'm not going to show the units though because I'm going to run out of room. 1 over 6 plus 1 over 12 plus 1 over 36 plus 1 over 18. Great. So you can find a least common denominator here. It would be 36 and go from there. But again, if that's not something that you love doing, I'm going to do it kind of the calculator way. So what I'm going to do is I'm just going to add all of these numbers in my calculator, add all these fractions, and see what it gives me. When you do that, 1 over REQ is equal to 0.3 repeating. So let's go with 0.333. But again, just like before, that's not the equivalent resistance, that's 1 over it. So I'm going to put this over 1 and then flip both sides. REQ over 1 is equal to 0.333, is equal to, 1 over 0.333. Okay, REQ over 1 is just REQ, and then 1 over 0.333 is 3. 3 ohms. There we go. And one more time, when you add these resistors in parallel, the total resistance goes down. So notice that this 3 ohms is smaller than any of the individual resistances. How much power is dissipated in the 36 ohm resistor? So the 36 ohm resistor, we're looking at this box right here, which belongs to sort of this larger row that we've got here. Alright, well, we've got V and we've got R, so let's go to our rules from before, and again, we know V and R, so what I'm going to do is I'm just going to go through all these till I find one that works. Do we know V and I? No, we don't know I, so that won't work. Do we know I and R? No, we don't know I, so that won't work. I think we know V and R, so let's do that one. V squared divided by R. Alright, V is, again, we're staying in this row, that's 12 volts. I know it's a little sloppy there, but it says 12. Over a resistance of 36 ohms. See what that gives you. I got 4 watts. My final answer. I'm going to box all my answers. There we go. Alright, so that's just some more circuits practice for you. At this point, go ahead and try that the quest assignment, which would be the bulk of the grade for the unit. Again, I'd like to get at least an 80. If you have any questions on those specific problems, then just email me, tell me which problem it is, and I'll get back to you with some kind of response that'll hopefully help you get through it.